Let's do this example 2.21. Okay, so here the question is this. If you have the book, you can take a look. If not, no worry. Okay, so example 2.21. All right, so this is the oops. So this is the question here. This is our question. So don't worry about other two. Let's talk about this here first. You have a system like this. You can see J1 here and D1 here, and this is gear location, right? This is the gear location. So input gear and output gear here. So N1 and N2, and on the left hand side you have theta 1. On the right hand side you have theta 2. Okay, so J1 D1 theta 1, and the torque on this shaft is T1. On this shaft is T1. So similarly, you have theta 2, and you have a J2 on the right, then you have D2, and also you have a spring here, K2. This is your question. Now the thing is you have to figure out theta 2 over T1. Now help me here. How should I reflect this guy? Should I reflect from left to right or right to left? Should I go from here to here or from here to here? Anybody can help me here? So I want to go to theta 2, right? Because that's my goal. Okay, theta 2 is the goal. That's why I want to reflect from left to right. Okay, everything from left goes to the right. Okay, that's my goal. So when I do that, so I'll start with this equation, right? So always, if you want to reflect, this is always the equation we have, because I want to reflect in terms of theta 2. You have theta 2, you have T2 here. Okay, I hope you are not surprised here, because remember, how do I get this on? Sum of impedances connected to theta 2 times theta 2 equals sum of applied torque at theta 2. Okay, sum of impedances connected to the motion at theta 2, then sum of applied torque at theta 2. Okay, so using this, so theta 2 is here, and T2, this is T2, we have only one torque here, right? So yeah, at theta 2 we'll have only one torque eventually. So then the sum of impedances. So there are three kinds of impedances. One comes from inertia, the other one damping, the other one is spring, right? So that's what it is. Now using this, I have to find the theta 2 over T1. So we have to work in terms of theta 2, meaning you have to, translate everything towards the right. So how do you translate this J1 to right? J1. How do you translate J1? Help me here. Destination over? Destination, what is destination? Destination is N2. This is N1, right? So N2 over N1 is square J1. That's how it transfers to the right. Then similarly, how do you transfer a D1? In the same way, your D1 gets transferred like this. Destination over source square d1. Okay. All right. So then on the right hand side, what do you have? J2. That's why you have to add J2 here. And you have D2 also. That's why you have to add D2 here. Then K2. So K2 is K2, right? Because there's nothing there. K2 is K2. So this is K2. KE is K2. That's what I meant. So JE is, as you saw here, JE is J1 N2 over N1 square plus J2. And DE, similarly, we have DE. Then KE. Then how about T2? So how do you translate this T2 to T1? Because I need T1, right? See that? I need T1. Theta 2, we did theta 2 part, right? Theta 2 part is already done. We change everything to theta 2. Now you have to do the T2 part. So how do you do the T2? How do you change your T2 to T1? So T2 equals T1, N2 over N1, right? That's the relationship. Now you just plug in here. You just plug in. So this T2 is T1 times N2 over N1. Then what is your theta 2 over T1? Theta 2 over T1 will be, so theta 2 over T1, right? So T1. So you have to divide by T1. T1 cancel out. Then theta 2 over T1 equals N2 over N1. Divide by this whole thing, right? S square plus, oops. S square JE plus SDE plus KE. Now you just plug in the value of JE, DE, and KE, which are this JE, DE, and KE. Then that's the answer. Guys, question here.
Yeah, I had a little bit of tough time following that. Can you explain again how we get the individual J, E, D, E, and K, E values again?
So you mean this guy?
Yeah. So is that that's just a formula that we this is a formula we went over last week, right?
Right. Yeah. Okay, not a problem. I can do that.
Yeah, that'd be great.
Okay, no problem. So let me go back a little bit to the slide, what I did last time, then I'll come here again, okay? So let me show you what I did. So here, see that? So if you want to change, this is the factor you have to, if you want to translate, you have to do this. Number of teeth of the gear on the destination shaft over number of teeth of the gear on the source shaft is squared. This is the translating factor.
Gotcha.
Okay, so now we have to use that here too. So here, right? So here, my goal is to get to theta 2, right? So that's why I want theta 2, but I have to change everything else to the theta 2 from left to right, right? Theta 2 is on the right side. So J1 goes to right. So when J1 goes across gear, right? This is gear. This is gear. So this is your destination. This is your source, right? We are going from left to right. So that's why you have destination square over source square, right? So your J1 will transfer like this. Destination N2, N1 squared, then J1. Your J1 becomes like this. Then similarly, D1 becomes N2 over N1 squared D1. Now the total, then total J is this plus J2. Because J2 is here on the right hand side. You don't have to translate, right? It's already there. So J2 is J2. So now you have two terms, one from the left, this is from the left, and this is on the right. So you don't translate it. So it's there. Similarly, D2 also, D1 also has to be translated to the right hand side. So this is, actually this is D1, okay? And then you have D2 here on the right. So we don't have to do anything there. Similarly, K, you don't have to transfer anything from left, right? Just only one. The K is only on the right side. So You don't have any change there. K is K2. Similarly, T2 is, this is the formula, right? Because T2 over T1 equals N2 over N1. This is always true, right? Then from here, you get T2 equals T1 N2 over N1. Does it make sense now?
Yeah, that makes a lot more sense now.
Okay. Thank you. So, all right, let's move on to the next slide then, okay? So let's do this. Problem 27. So this is from the book, okay? So you are given a, so you are given this question here. Problem 26, for the rotational mechanical system with gears as shown here. So this is rotational mechanical system. This guy rotates, but you have gears at two locations. Location here. This is the location where you have gears. This is where the location, this is the location where another set of gears is, okay? So this kind of system is called gear train, okay? You have more than one gear system, so gear train. All right, so this is a gear train system having gear train rather, okay? All right, so let's look at this guy here first. Look at this location here. So here you have N1 on the left hand side, right? This is N1. On the right hand side you have N2. Okay, left N1, right hand side N2. Then left hand side you have J1 and D1, okay, related to this gear, and J2 and D2 related to this gear here. Okay, so then on the left hand side you have T1 equals T, theta 1 equals theta. On the right hand side you can say T2 theta 2 in the same way. Okay, but these are connected. These are connected. Now you have the second location here, another location where you have gears. So if you are here on the left, you have N1, just next, right next to it. Right next to it, you have N2, N3, J3, and D3. Right next to it. Then right next to this guy, on the right hand side rather. So you have N4, J4, and D4. Okay. Similarly, you have this is again, this is inertia, right? This is inertia. This is just the inertia, okay? Inertia, and also you have damping there, inertia and damping. So this is the question. So now your goal is to figure out D3 over T. So what is D3? D3 over T. You have to find this one. T is this. What is D3? D3 is, sorry, what did I say? Theta 3, sorry. So theta 3 over T. That's what you need to figure out now. So what is your goal now? Your goal is to transfer everything from here to here. So let's do one at a time. So let's transfer. So from here to here first, right? Then we'll do it from here to here directly. We'll jump one step here for that, right? So let's finish this, then we'll do that. So from here to here. So what is this J2 become? J2 and D2, what do they become when you go to the right hand side from here? So not only J2, D2, you have J3, D3 also. See, this is the entire system gets transferred, right? Does it make sense? These two and these two get transferred from here to here. So meaning you have J2 plus J3 get transferred, and D2 plus D3 will be reflected to the right. So how do they reflect? How do they get reflected? Again, this destination over source square, right? So what is the destination here? N4. What is the destination here? N3, right? So N4 over N3 square. Similarly, here you get N4 over N3 square. That's question here so far. Now, so we talked about this. Now, before I move on here to here, okay, I find the relationship between T3 and T1. Let me find the relationship between T3 and T1. Then I'll do this jump here from here to here based on this. Okay, so it makes your life easier. So what is the relationship between T2 and T3? What is T2? This is T2, right? What is T3? This is T3. Let me erase everything else. It's messy. So we have this guy already, right? We have this guy and this guy. Okay, we already have them. Now T2 to T3, when you transfer this, reflect this rather, from T2 to T3, what do you get? You have the relation T3 over T2 equals N4 over N3. See, this divided by this, that divided by, okay, this is the other way around, right? So this divided by that, this divided by that, they're equal, right? So how do you change, so how do you, let's say, how do you write in terms of T2? T2 is, sorry, in terms of T3, T3 is N4 over N3, T2, that's what we have. Now similarly, what is the relationship between T1 and T2? This is T1. What is T2? This is T2. What is the relationship between these two? So T2 over T1, which is T, equals N2 over N1, right? So then what is your T2 then? T2 is N2 over N1, then times T. So now your N4 over N3 is there. Then you can plug in your T2 now. T2 is this guy here. This guy comes here, which is N2 over N1 T, or T1, or simply T. So if you go from T2 to T3, what do? You do N4 over N3, right? If you go from here to here, what do? N4 over N3, N2 over N1, right? This is the case of T, torque, right? Now, in the case of Z, what did you do here? In the case of J, you do the square, right? See that? In the case of J and D, you do the square. In the case of T, you simply take N4 over N3. In the same way, now give me the answer here. Now, in the same way, if I go from if I go from here to here, so theta 1 to, not theta 1, so J1 D1, I'm going to take J1 D1 to all the way to here. So how does my J1 changes? How does it change now? Help me here. Guys, I'm lost. I need your help. Please.
It's not N3, sorry, it's not N4, but N3 times N2 of an N1, is it?
Exactly.
Gotcha.
N4, N2, N3, N1 squared. So this is the rule. If you reflect your torque, right, you simply multiply by this. If you reflect your J and D, you have to multiply by the square of that. That's the thing. Okay? So that's why your J1 becomes that now. Similarly, your D1 becomes this. Now everything is on the right hand side now. Everything is on the right hand side. Now you have to add them all together. Okay? So you have this guy on the right hand side, this guy on the right hand side. Then what else is there on the right hand side? You have J4 and J5, right? So that's why you have to do J4 and J5 also. That's the total. Similarly, in the case of D, what do? So these guys are already reflected to the right. Now what are you left with? You have D5 and D4 left. D5 and D4 left. So that's your JEQ. By the way, this is your DEQ. That's your DEQ. Okay, so then what do you do? What do you do next? Then you just plug in everything here. JEQ goes here, DEQ goes here. What is your KEQ, by the way? Oh, there is 0 because there is nothing there, right? Is there? No, you don't have to. You don't have to worry about this guy. Then theta 3. Then T3 you have to change like this. T3 is like this. This goes here. Then you have T in here. So theta 3 over T, right? So that's how what you figure out. Done. The main step is how to reflect to the destination. That's the main thing. Question here? Please, any comment, question? Emery, Jane?
Nope, I think I'm good.
Lucas, any comment, please?
I think I'm all set too.
Okay. LJ? Saad? Nick?
I'm good.
Okay, thank you guys. So let's move on then, okay? All right. All right, so this is just a physics, because I need this for the next topic. That's why I just put it here. So this looks very simple to you, I know. So physics 112, right? So if you have, I'm not going to go in the detail. Suppose this is the magnet, right? This is the magnet, north and south, you can see here. This is the magnetic field. This is the magnetic field, the red one. Oops, let me change it to something different. So these are the magnetic field. Okay, good. So happy to hear from everybody. Oops. This is the magnetic field, right? This is the magnetic field. Goes from north to south. Okay. Then if you have the current carrying conductor, this guy, this is the current carrying conductor. See this one. This is the current carrying conductor. Okay. So then what is the force on this conductor? Force on this conductor. The force on this conductor is given by V. What is the field here? What is the field? V I, the current passing through the conductor, right? Then L, what is the length of the conductor here? Length of the conductor meaning from here to here. From here to here. What is the length of the conductor from here to here? That's the L. Okay. So you have B, you have I, you have L, then theta. So what is the angle between this conductor length and the B, right? So if you get 90, then you get maximum force, right? So theta is 90, and you get, so F equals BIL is the maximum force. Okay, so this is just physics 112. Similarly, how do you get the, in the Faraday's law of induction, what do you get? So what is the, so this is the, what is this thing? Magnet. So you have the coil, right? And you move the magnet. Move the magnet back and forth, okay? This way. Move this, no, this way, that, so this way, move the magnet back and forth. What happens? Then there is change in flux through this coil, right? Okay, and back EMF is produced there, right? Back EMF, and that back EMF is given by BLB. Okay, so where B is the magnetic field, L is the length, and V is the velocity of the magnet, right? So this is the and actually, yeah, there is negative sign because that negative sign is given by Lenz's law, right? Remember Lenz's law. So this kind of stuff. So you need to understand this. EMF equals BLB. Okay. Similarly, this is another part in physics 112. Physics 112 again. So what is the torque? Torque experienced by the coil. So this is the coil here. See this rectangular coil? This is the rectangular coil. Is on the magnetic field, right? Magnetic field B. Then what is the torque experienced by this coil? So torque is tau, is NIAB sine phi. Okay. So what I'm trying to say here is torque is proportional to current I. That's what I'm trying to say. Okay. This is the number one. Number two, EMF is proportional to velocity. Okay. So here I'm trying to say EMF is proportional to velocity. I just need these two relation. Okay. So try to remember that EMF proportional to V and tau proportional to I. Because we assume that, so we can say that, right? We can say this because if V and L are constant, right? We can fix them. Suppose you have a constant field, right? If your B is constant and L is length of the conductor is constant, then you can say EMF proportional to B. Can you say that? Similarly, here, if the number of turns, here, this is the rectangular coils, so the number of turns is N, right? N turns. Number of turns is constant. Then A, the area, this area is constant. Then B, the B is constant. And phi, we usually take this 90, right? So this phi is 90, so it is constant 90 all the time. Then you can write this guy as tau proportional to I. So I made two conclusions here. Tau proportional to I, EMF proportional to V. Okay, please try to remember these two things. EMF V, tau I. Let me write this down here. Here, somewhere. EMF proportional to V, tau proportional to I. Okay, I need that. Okay, so now after that, I'll move on to the next topic now. So electromechanical system transfer system. So this is the last one. So with this, will finish the chapter 2. This is the longest chapter of this course. So hopefully we'll finish this tomorrow. Then yeah, you guys will have a homework today or tomorrow. I'll assign the homework that will be due next week. All right, so electromechanical system transfer function. So we'll be doing again the transfer function, but the system is hybrid of electrical and mechanical system, because we did both electrical and mechanical, right? So we did electrical, we talked about L, R, and C. Then mechanical, so we talked about translation, we talked about rotation, then we talked about rotation with gears. Okay, so now we mix them all together, we combine all together, and we call it electromechanical system. Okay, so electromechanical system is very useful system. As you can see, this is one of the examples that I showed here. This is the NASA flight simulator robot arm, and it has electromechanical control system components. Okay, electromechanical control system component. This is just an example. We have lots of examples like this. So, all right. So first of all, we'll talk about armature control DC servo motor. Armature controlled DC servo motor. So have you guys seen how the DC motor work? Guys, any comment here? Okay, so this is the schematic of DC motor. Actually, this is the small cartoon or GIF, whatever you call it. So here we have the magnet. This is the north pole. You can see here, this is the north pole of the magnet, and this is the south pole of the magnet. So the magnet is fixed there. Magnet is fixed. That's why your B is constant, right? B is constant. Okay. So then you have the coil here. You see the coil? So you have the magnet, and in between, in the middle, in between the magnet, rather, there is a rotor. See, this is something that rotates. This guy, this guy, this is called rotor, right? This is called rotor. Something that rotates. That's the rotor. And you have the coil around the rotor there, right? You have the coil. So this red thing here, this is the coil. Okay. So this is what it looks like. So now our motor is armature control. What do I mean by armature control? So armature control means we change the current in the armature. Okay. So there are two kinds of DC motor. So before I go there, before I move here, so let me explain this picture first, okay? So this picture is denoted like this here. This is represented like this here, rather, okay? So you have the input voltage EAT, input voltage passing through armature resistance, then armature inductance, Then that passes through the motor, right? The rotor actually. Actually, this is the rotor. Okay, this is the rotor. Then you have a fixed field. So fixed field. So this is more simplified, right? This is more simplified here. If you look at this, this is even more simplified. So you have the field input voltage going through the current passing through the RA, armature resistance, armature inductance. Then you have the fixed field, which is magnet, right? Which is magnet. This is the rotor, right? This is the rotor. Then it rotates, right? Rotor does the rotation, right? So that's what it is. So it rotates with the the angle of rotation of the rotor is theta m, and the torque is Tm. Because of the torque, it rotates, right? There is no torque, there is no rotation. So there is torque, that's why you have rotation. So fixed field is the magnet, as you can see here, right? So the DC motor can be armature control or field control. So this is the field, right? See, this is the field. So you can create the magnet. You can have the magnet made of electromagnet. So you can use the electricity to make a magnet, right? Which is called electromagnet. Electromagnet, right? So sometimes you have the motor where you change the current in the armature. So sometimes you change the field here. Okay, this is field control. This is armature control. Okay, in our case, our field is fixed. So we change the current here. So we change the current on the armature. That's why this is called armature controlled motor. Okay. So motors are actuators. So most motors are actuator because actuators are something that makes the robot move, right? Or anything move, not only robot. So DC motor is powerful actuator device that delivers energy to the load. Okay. So this is connected to load here. This is load. So this is motor, and motor always connected to load, right? So this is what I'm talking about. Yeah, so this is it. So now let's find the transfer function for this system. Okay, this is the simplified a diagram of the motor, DC motor. Actually, this is a servo motor. Okay, there are different kinds of motor. This is servo motor. So armature controlled DC servo motor. That's what we'll be talking now. Okay. So now, so you have the input voltage here, right? This is the input voltage. So this current passes through this, and this guy rotates, right? This guy rotates. Then what happens here? So then you see the back EMF here. Faraday's law of induction. Did somebody leave? LJ. Okay, he's not here. Okay. So okay, so I was talking about. Yeah. So I talking about back EMF, right? So this is the back EMF. So here, what is the back EMF? Remember the voltage proportional to voltage, EMF proportional to what did you conclude before? EMF proportional to velocity, right? What did I write that? Here, right? EMF proportional to velocity. So in our case, the velocity is angular velocity, right? So how do you represent the angular velocity? Theta dot. Okay, theta dot is same thing like d theta over dt. Okay, we can write theta dot. So when there is the time derivative, then you can put dot. When you have, you know, with respect to x, then you call it y prime. Remember, we call it prime sometimes, we call it dot sometimes. Dot meaning with respect to time. Prime meaning with respect to x. Okay, so your BB is proportional to BB is proportional to theta dot. Now BB can be written as K times theta dot. So you can write B here because we will have other constant too. Okay, we'll have other constant in this problem. That's why I'll call it KB so that we won't have any confusion. Is it boring? Everybody's leaving now.
Maybe they're losing connection. Oh yeah, someone's back.
Okay. All right. So you understand this, right? So the back EMF is KB times theta m dot. That's your back EMF. So now, so how do you, what is the Laplace transform of this guy? What is the Laplace transform of this guy? Help me here. I think you can help me. BBS equals KB is constant. It doesn't have Laplace transform, which is constant, right? It's the same, right? So what is the Laplace transform of this guy here? Guys, please help me. I'm lost. Right? Okay. So we have one equation here.
So wait, sorry, just a quick question. So the Laplace sorry, the Laplace transform of a derivative is just not derivative?
Remember? So
I guess I'm having just a little trouble remembering.
yeah, that's fine. DF, if you wanna do the Laplace transform of this guy, this will give you S times big F.
Ah, okay.
Right? So this is, I don't know how to make big theta here. You understand, right? This I'll write simply S here. All right.
Right. Okay, thank you.
All right. So guys, sometimes you have to wake me up. Okay. All right. So now this is what I got. So I have the, so this is the Laplace transform of that guy. So we got that, right? So now, okay, so what else we can do here? We found the Laplace transform of this guy, BB, right? We found that. Then this is this, right? Laplace transform of this guy. Then what is Laplace transform of this guy? LA. SLA. So what is Laplace transform of RA? Simply RA, right? It doesn't have any RA. So what is the Laplace transform of this guy? Big EA. Yes. Laplace transform of this guy is big EAS. Laplace transform of this guy is simply RA, doesn't change. Laplace transform of this guy is SLA. We know that, right? So the Laplace transform of this guy is this guy here. That guy. Now you can use the, what can you use here around this circuit now? What is the law? Help me here. Kirchhoff's voltage law, right? So let's use the Kirchhoff's voltage law. So what do you get here? So you start from here, right? You start from here, let's say. So this is you have EAS. So you have RA. Then you have RAIA, right? Sorry, RAIA. Then LA, SLA, IA. Then you have BB, S equals 0, right? So BB, so here you have this guy is that, then this guy is that, this guy is that, then this guy is that. That's all, right? We don't have anything else. Now choose the sign. If you go from here to here, you are going uphill. This guy is plus. If you go from here to here, see the current flows like this. See, this is plus. Current comes out of plus, so this is directional current. So you are going downhill because current always go downhill. This is minus. And you are going downhill again. This is minus. You are going downhill again. This is minus. Make sense? Then you can take this to the right hand side. So RALA, LASIA, BB on the right hand side and EA on the left hand side. So that's what you get using the KVL. Question here. Question, please.
I think I'm good to go.
Okay, nice. Now, so what is the next relation we have? So we got two relations. This is the first relation we got. This is the second relation we got, right? There's too many green colors here. Let me make it red. So that gives you contrast. This is equation 1, this is equation 2. Okay. Now, what I'm trying to do here is this. Let me erase. Oops, I don't want to erase that. I don't want to erase that. Tau proportional to I. I don't want to do that. Okay. Now the third is you wanna use this relation here. Tau proportional to I. The torque here, right? Because the thing rotates like this. Okay, I think this is the good one. So see, this guy rotates here. The torque, that torque is proportional to the current here. Whatever current flows here is going to affect this TM. So that's what it means. TM proportional to IA. Okay, since TM proportional to IA, so I can say TM equals KA. For some, I simply call it KT. How about that? KTIA to be consistent with the book notation of the book. Okay, so TM equals KTIA. That's what I have here. So from here, what do I get? Can I rewrite this guy as IA equals, divide both sides by KT? So this cancels, so divide out, so IA equals TM over KT. TM over KT. Now the thing is, what do we do now? So I call this 3. So did you lose connection?
Yeah, my internet shit the bed real quick, so I'll just hop back in if that's okay.
Okay.
Yeah.
All right. So, oops. So here now, what do you do is I plug in here now in number 2. Plug in 193 and 2. So goes 1 here, goes 3 here. So 3 is this guy, 1 is this guy. So meaning Your RA is RA. Then oh, you know what? Let me simplify this a little bit. How about that? Let me simplify this number 2. Can I simplify like this? RA plus LAS IA plus BB S plus equals EAS. Does it make sense? Okay. So RA plus LAS is here. Then what is your IA? IA is TM over KT. TM over KT. That's your IA. Then what is your BB? BB is, help me here, KB as theta. KB as theta. That's your BB. Then you have EAS on the right. You have EAS on the right. So far, so good.
Yeah.
Now, here is the tricky part now. A little bit tricky part here, okay? All right. So let me make it clean. All right, so here is the tricky part here. Now, what I'm going to show you here is, I'm going to talk about, okay, so what is your goal? Your goal is to figure out transfer function, right? So what is transfer function in this case? My transfer function is theta m over EA. That's what I'm going to find. Okay, theta m over EA is my transfer function. That's what I'm going to find here, okay? That needs to be found. Okay, now how do you do that? So EA is here, good news. Theta m is here, good news. S is Laplace transform, Laplace space variable. KB is constant, we don't have problem here. KT is constant, we don't have problem here. RA is constant, we don't have problem here. LA is constant, we don't have problem here. S is Laplace transform variable again. Now the TM, this TM guy, this is bothering me. So TM is what? TM is the torque. It's not constant, right? Remember? Torque depends on the current. So this is the relationship between torque and current. Now, my claim is that not only the relationship between torque and current, there is also the relationship between J, D, and torque. That's my claim now. Torque is also related to J and D. What do I mean by that? What do I mean by that is this. What I'm trying to claim is this. Impedance, total impedance, remember total impedance times theta m equals Tm, remember? That's what I'm trying to claim here. So sum of impedances connected to the motion at theta m times theta m is equal to, which equals sum of applied torques at theta m. That's what I'm trying to impose now, use. This is the relation I'm going to use. And I claim that there is a relationship between Jm, theta m, dm, and Tm. So Tm is related to dm and Jm. Tm is also related to Ia. There are two relationships for Tm. Okay, that's my claim. So let me verify, let me prove my claim then. So let me prove it. So let me use this formula. Then what is the total impedance here? So can you help me figure out total impedance? So total impedance is, when I say total impedance, When I say total impedance, this is what I meant. So total meaning, so this guy is connected to, okay, this guy is connected to load here, right? This is your load. Load means something it drives, right? The motor will drive something, right? Otherwise, it's, you know, there is no point of having motor, right? So there is a load that drives, that is driven by the motor, right? So that is your load. So when you talk about, so the equivalent, remember we talked about equivalent here. So what is the relation there? JE S square plus DE S theta M equals tau TM. That's what I'll be talking, right? This is what I'm talking about. This is the relationship I am talking about. So there is no spring here, right? Do you see any spring? There is no spring. That's why you don't have to take that spring into account. But there is definitely there is a mass, right? Anything has mass, so that's why we have inertia, right? How about viscous damping? How do I know that there is viscous damping? I don't see any damping here. Do you? JE, not a problem, because JE always, if there is mass, there is inertia, right? So you cannot have a system without mass. So JE is always there. JE S square, not a problem. This guy is not a problem. So we don't have K, spring, there is no K. So K is 0, that's not a problem. The thing is, how did I know that there is viscous damping?
Friction? Is there friction in it?
Yes, because you know what, how the damping is related? Damping is related to what? Damping related to V, right? That's the formula, right? So what is the formula for damping? You have a dm times velocity, right? So whenever there is velocity, there is always damping. Keep that in mind. Okay, if the system is moving, there is always friction, right? You're right, Jane. Okay, so when the system is moving, there is friction, meaning whenever there is velocity, there is always D there, damping there. So that's why you have two terms here, but no K. Now the question is, what is this theta M and theta TM? What is this theta M and TM? So TM is the, TM is what? Torque on the motor, right? Motor, right? Okay, guys. So when I say TM, so what is the role that TM plays? What does this TM do? The TM not only moves this rotor, but this also moves the load, right? Do you agree, guys? So this is very critical here. You have to understand this. I'm waiting for a question. So let me say it one more time. So TM is the torque of the motor, right? So what does this motor do? What does this motor do? It does two things. One, it moves this guy, armature, right? This is armature or rotor, right? So this TM moves rotor, and also this TM moves the load. So that's why you have to take both into account. You have to take the load and rotor into account. That's your TM. Does it kind of make sense? Not really. Guys, if you ask me a question, it will be easy for me to, explain it better. So be frank and ask any question.
So now that we have now that we've gone through all the electrical stuff and we have the equation for that, we have to look into the motor and see what it's driving, and then find the equation that Tm is equal to and put it into the electrical equation?
Yes.
Cool. I think I get it.
Good. Yeah, so Tm, now this is your Tm. Now Tm is this, right? So what I'm trying to say is this Tm has two parts there. One part due to armature part, and the other one is load part. Okay, even though I call it Tm, right? When I say Tm is motor, right? But even though I call it motor, there is load there all the time. What's the point of having motor without load? That's why you have to take load also into account. So load plus armature makes the motor. So in other words, this Tm not only move the armature, but also it has to move the load. That's why it has two components. All right, so I'll talk about that later in detail, more detail. But for now, what I want you to keep this in mind, that this M has two components. This has two components, this has two components, and this has two components, okay? But this is total, right? Right now it's total. This is not a problem, because how did you get this? Using this relation here, using this relation, right? JES squared DES theta M equals TM. That's all. Okay, but in the next slide, I will need that this guy consists of two parts. All of this consists of two parts. Okay, so in next couple of slides. Now, okay, all right. So I carried these two guys from the previous slide. Okay, I carried these two guys from the previous slide. Okay, so now we have to combine these two. Here we have to combine. How do I combine? So remember this Tm, replace this Tm by this guy now. So what do I get then? RALAS, Tm is this guy, JMS squared dm theta m, JMS squared theta m dm. Then KT is KT on the bottom, then KB this, and EA on the right. Make sense? Now we're finally in a position to find the theta m. So theta m over EA, that's our goal, right? Theta m over EA is the goal. So theta m also. Now in this case of armature control DC servo motor, this guy is very, very small. Okay, that's why you can simply neglect this guy. So if you neglect that, what do you get? RA JMS squared DMS, RA JMS squared, see that? JMS squared DMS, then you have then S theta m is there, then you have S theta m from here too. That's why you just push this KB in. So you just factor out this guy, and EA is on the right. Now we got, from there you got this theta m over EA equals what do I get? 1 over so let me show you what we get here. So theta m over EA equals, right? Theta m over e is 1 over s, 1 over s times Ra over kt jms plus dm plus kb. That's what I got. That's your theta m over a. Now, if you just remember, you get rid of this jm Ra over kt. Remember, we used to do that, right? You get rid of jm Ra over kt. If you do that, you'll end up getting this. This is simple, a couple of steps of algebra. 2 steps algebra. Gives you this. Okay. I really hope that you can do it. All right, now this guy, look at this guy now. What is here on the top? You have KT, RA, JM. They're all constant. So what is on the bottom? So this guy is constant also. JM is constant, DM is constant, KT is constant, KB is constant, R is constant. So this guy is in the form of BK. I'll call this BK. This guy is BK with no subscript. Then you have S plus alpha. S plus alpha. This is alpha. Now looks like our equation is in very, nice form, where K is, we have the form of K over S plus alpha. We just have two constant K and alpha. Okay, looks in the very nice form, but the thing is, this K is this whole thing here, and the alpha is this whole thing. Looks like nasty now if you look at them. Okay, to figure out that, so now to figure out K and alpha, right? To figure out K and alpha, now we go to the next slide. Now we are our goal is to figure out K and alpha. Okay, now remember that JM was what? JM has two parts, JA and JL, right? Remember, I called it last time. Then you have DM has two parts also, DA and DL. Okay, so because you have to take load also into account, not only the motor itself. So we call now two parts, and one part is from the motor, which is JA, and the other part is from the load. Okay, similarly with the viscous damping also. Okay, now we can represent this kind of situation in this picture here like this. So you have the motor. In the motor side, you have JA, on the other side, you have the load. Load has DL and JL. Then in practice, motor and load always connected by gears like this. Now your goal is to figure out the JM and DM, right? That's your goal. Your goal is to figure out DM and JM. JM, which has two parts, DM, which is two parts. So you have to figure out this guy, these two. Meaning you have to jump here. Now you have to go there now. So how do you get there? So you don't have to do any. So what does your JL become here? You guys have to help me here. What is the factor here? When you go to the right.
Would it be N2 over N1?
Remember, destination over source.
Oh, we're going from right to left, right?
Yes.
Oh, so it'll be
You
N1.
said from left to right, confused me.
Huh?
You said from left to right, so I was confused.
Did I say left to right?
Yeah, so I was lost.
So sorry.
Oh, gee.
I'm so sorry. Remember, we need to do the JM, right? It has two parts, right? JM has two parts. So we're talking about this right to left. Thank you for the correction. So what did you say? Can you repeat this one more time, please?
Oh, would it be, wait, sorry. It's driven over driver, right? So N1 over N2?
Yeah, no, over, yeah. So destination over source. So what is your DL? The DL becomes in the same way you have N1 over N2 squared. Now, then what is the total then? The total is JL this plus J, because J is here, you don't have to do anything. Then DL is this, then you have DA, you have to add this together. Now, this is how you change your, this is how you get your JM and DM. So now you found your JM and DM. So let's go back here. Now you found your JM and DM here. So you found your JM and DM. Okay. These guys are done. JM, DM is done. Then what do you need to find out now? KT, KT and KV, right? Now you need to find KT and KV. So how do you find KT and KV? We'll do this tomorrow, next time. Guys, question? Any questions so far? I'm ready to answer. If not, I'm done for the day.
All right.